kind of pop wisdom, maybe even. It's going to be a bunch of vignettes on how to work with heavy tail data. And just by way of background, let me just say, first thing to say is that this material was recommended to my co-author and I, Omar Guerrero, many of you know, to add this to our book manuscript. Several reviewers of that book manuscript said that economists don't know very much about this material, so that practical issues that I'm going to show you today is just kind of a bunch of examples and things about how to get up to speed on this. But I think maybe more kind of importantly vis-a-vis our PhD program here is that floating around CSS for at least for more than a decade. Actually, when I think about this, this was a conference that was run in the early aughts, when way back when CSS was just forming, and about power laws in the social sciences. And this was a book with many eminent contributors. I mean, people like Brian Barry, who's a theorist of cities, and just Thomas Lux, who's a good finance guy, and Don Parker was writing about land use sizes, that kind of thing. So this was a whole book about the application of power law ideas to the social sciences. Now, there's some theory in here that, I'm not going to go through all the entire book or anything, but the idea is that many of the same techniques that I'll discuss today actually are in this book manuscript. They never got published. And there's a long history about why this is the case. I'm not going to rehearse that history here. So Andrew's laughing in the back, and he knows the story, and the story's not looking good. Make a long story short, though, is that I believe that we have some version of this in electronic form. So I'm going to pass this around. You can look at it at your convenience. And if anybody wants a copy of this, we can get you some version of it. It's not going to ever be realized, at least in this current form, by the publisher. It's also the case that in CSS 625, much of the material in this book is covered. Now that course is complexity science, or
Theory of Complex Systems.
Theory of Complex Systems, taught by Ken Comer, who has a degree from SCOR, but does a lot of work on EGRS models and complex systems. And so, if you want to learn more about this kind of stuff in particular, today I'm going to primarily just work on the techniques, show the techniques, but if you want to learn more about the applications as well as the techniques, Ken's class will be taught in the spring. Mm-hmm. So if you want, and I know some of you have taken that class also. Okay, so once again, I said the motivation here is just to kind of give just some background. And so what I'm going to show today is going to be a little bit specific, and it's going to be tied to economics and finance data, but the techniques are broadly applicable. This is not going to be a kind of systematic thing. I'm not going to do a ton of mathematics, like go through a bunch of derivations and definitions. I'm really going to show what I think we would call maybe just more like kind of useful rules of thumb for dealing with large data. And I also intend to do a little bit of live work on a machine here, but we'll switch the thing back and forth as we go. Okay. So heavy tails. What do you mean by heavy tails? I'm going to get just a little bit more specific, but here's the point of departure. So think about in particular, think about some economic variable. Think about even like the size of cities or the size of business firms. So the data that take on some positive value, and I want to say that when we think about these, they're skew distributed. So the real counterfactual is not going to be today looking at the Gaussian as something which is not heavy tail, because the Gaussian can take on negative values nominally. We're going to imagine thinking about kind of if we're going to think about the exponential distribution, maybe is one of these things, but it's not going to necessarily have heavy tails, which I'll get to in a second. But if you think about this, there's some skew distribution in which we typically are going to have decreasing numbers of larger things. Okay, so there's a few large cities and there are a lot of small cities. There's a few giant firms, a bunch of small firms. There are a few days in the New York Stock Exchange where things fluctuate a lot, and most days things fluctuate a little. So think about it in those kind of terms. And I've written those examples here: income, wealth, firm size. Many things follow this. Now I'm going to get into a discussion in a minute. Joe's here about whether these things are common or rare, but we'll come to that in a second. The main thing to say about this, the main reason why it's really kind of a separate topic from normal, or why you oftentimes don't encounter it in a normal statistics class, is there are certain pathologies associated with these things, and we're going to get into it. And at least kind of one summary way to kind of describe many of the pathologies is that the moments of these distributions may not exist. Okay, and we'll get into what that really means. But think about it. It's a distribution. We're used to thinking about if we just take everybody's height in this room and figure out what the average is. It's going to be 5'6" or 5'7" or something. You're going to be plus or minus a couple inches, right? There's no question about the moment does not exist. The first moment doesn't exist for that, or the variance is well defined, etc. So for many normal data series, we're going to always have it be the case that moments exist. But now today, for everything we do today, we're talking about data for which the moments are problematical somehow. Okay, now we'll get into the idea that for any finite data set, you always can compute the moments, but they just may not be meaningful. Okay, so that's kind of the point of departure here. All right, everybody okay with that? All right, so I'm just going to. So yeah, here's this paper from a year or two ago by Closet. Our power law is common. Okay, so this, we're in the world of heavy tails, and we'll get to what power laws are. Are these kinds of data common? And it's I think a general idea for a while that no, maybe the things that are Gaussian are more common, because we have the central limit theorem telling us that if a bunch of random stuff will become Gaussian. So that's once again, painting with a coarse brush, we're going to see things that lots of things are Gaussian. But then people who work in complexity say, well, holy cow, heavy tails are everywhere. Heavy tails are in firms and cities and prices and et cetera, et cetera. So maybe they're common. And in this paper here, from a year and a half ago, they assert that, at least according to some very specific statistical tests which they have formulated here, they say in fact they're not very common. That if you test, you're going to get some deviation from it. So we're not going to be too concerned here today about the metaphysics of is it literally a power law or not. We're going to just be concerned about, for example, things like does it have heavy tails and do the moments diverge or not? Okay, so we're not going to be too hung up on the metaphysics of is it literally a power law or not. You can imagine data. We're looking at real data, and data which are characterized by a few large events are going to oftentimes have a lot of noise in them, and those noise can skew such analysis. So we can get back to this at the end if you want. I think Joe has informed me that several people who had run around the world before 2018 claiming power laws are ubiquitous take issue with this paper. Okay. But for now, we'll just take my face value. How common though are these are heavy tail phenomena? So what I want to do now is just show you guys at least some. We're just going to look at kind of pretty pictures here. So from this book that Omar and I have written, we have this is basically what I'm going to show you first here is just a bunch of data on firm sizes, okay, and how skewed firm sizes are. Many of you guys have seen this before, so just bear with me here. But basically, so firms are this is a histogram now of firm sizes and how frequent they are. And so there's a few firms that are giant and lots of firms that are small. And this is an example of something that looks like it definitely has a heavy tail. Looks like it's a power law distribution. It may not be by Closet's criteria, but it's at least heavy tailed. But now it turns out other things like we can say, what about the firms not by the number of employees they have, but by how many what is the number of receipts they have? How many sales do they have? We get another power law. Then you can say things like, well, receipts are the output of a firm. The input of a firm is going to be the number of workers. So the ratio of those two things are the productivity. And so in productivity measure this is now for every firm in America. This is a distribution of now the right tail. So just looking at one tail for how much productivity there is. Now the modal productivity in America is that a typical firm produces about $100,000 of sales per worker. Okay, but notice that this is very fat tail out here, which they said there's some firms that produce $1 million of output per worker. There are a few firms that produce $10 million per worker. I mean, really weird firms that produce gigantic amount of output. Now the main thing to say is that we'll get into this in a second. The fact that we're getting a quasi-straight line here in these log coordinates is a symbol that we have some heavy tails going on. Okay. Now many of you guys have seen these data before, so I want to show you data that you have not seen before, which is we have only recently got the data for the financial aspects of these same firms. And so I want to show you kind of a cross-section of a whole bunch of things here. So for example, if you look at what is the distribution of salaries and wages paid by firms, you get another power law. Once again, the dots are showing it's not a pure power law, but it's something that's very heavy-tailed. Then we can look at things like, some other things are going to be, how do firms compensate their executives? That's another quasi-power law. A little bit more, see some curvature here, some heavy tail. And this one's going to be log coordinates. And just, the main point of these plots is just to show you that these kinds of things are widespread in the economics and finance world. This is how many taxes are paid per firm across all 6 million American firms that pay taxes and have employees. See another kind of heavy tail, not a pure power law, but something that's heavy tailed. And it's include on one or two things here. Look at the even things like the assets of firms, which are much more static. Assets of firms are also have this flavor. Okay, so by a wide variety of measures, we're going to find these things all over the place. And the question is now, how can we characterize them, deal with them, how can we best understand them? And that's what I'll talk about here. Okay. All right. So now just some quick background. Then I want to change machines and go over and just do some quick numerical work. But I briefly mentioned that exponential distributions, which are skew, are not heavy-tailed. And here's the way that I found is the best way to communicate this to people who are not really familiar with the terminology before, haven't seen it much before. So if this is the density function for an exponential, and the mean is this, mean is well defined for this parameter. So if p is 10, then the mean is 1/10 or something. Think about the average life of an American firm is closely described by this. So p is about 1/10, meaning the average firm has a lifetime of about 10 years. Here's one way to think about about heavy-tailed distributions. Look at the value of the function for a certain size. Now for the next bigger size up. And if you compute these things, compute that across here, you basically get that. Well, for this particular size, you're just going to get that everything drops out. The pre-term drops out, and then this is going to be only off by 1. So exp of minus p is a parameter. P is a constant, some number. So that's just a constant. Okay. So when we were to plot, and I'll put a plot for you guys in a second, but so we're going to plot then the distribution, the density function here, f of the function of s, it's going to be declining, right? Monotonically declining. And the main thing is that the difference between any two successive values is always going to be, has the same ratio, right? So the height of that one compared to the height of that one, the difference is going to be exp minus p, and to that one also. So we're declining at a constant rate. So basically think about you're driving up. Think about the successive values here. You're driving a post into the ground. Every time you hit it with a hammer, you drive it a certain fraction. You keep driving it further and further into the ground. Okay, so you keep driving it further and further into the ground. Pretty soon, this is gonna go right almost to 0. And so there's going to be not a very heavy tail, as compared to the following, which is now this is the Pareto distribution. It has a different density function here. But the main thing to say now, if we look at this at two successive values, what we find is two successive values are going to be different by this amount, which is a ratio now of what the two sizes were. So if it's size 1 and size 2, well, this is 1/2, say. It's a fair size ratio. But as we get up to higher and higher values, this ratio is almost unity. So it's like we start driving the post into the ground, and the thing starts declining. The function starts declining here, but it's declining quickly initially, but now it's declining at slower and slower and slower rates. And basically, as you get to some very, very large value of the size, you look at 1 million. So this is now 1 million divided by 1,000,001. Every time you hit the post, it's not going anywhere. It's just going down very slowly, right? But it's going down so slowly that it's not actually going to converge, and so we're going to get problems with the moment. So if you could try to compute the first moment of this thing, you get this thing, and then it says that, well, if in fact that value of p is less than 1, we're in trouble, because now we're going to get a noisy value for what that mean value is. Okay. So once again, the paradigm for non-heavy tails is the exponential. Every time you go out to successively higher terms, it keeps going further and further lower at a constant rate. But the main thing to say is that the Pareto distribution has the property that as you go out to further and further large sizes, it starts getting smaller at an ever slower rate. Right? The rate at which it's getting smaller is slowing down. Okay. All right. So any questions on so far? So what I'm going to do now is just to switch over to the other projector. So this is the other computer. So maybe this dongle is the trouble. Okay, I don't think I can just do it on this computer. Have the exercise in here, but I'll just do it in real time. Okay, so I'm going to just demonstrate for you guys in just a couple of these basic ideas. All right. And once again, I think for those of you who have had 625, you've seen some of this stuff before. I'm going to do this with Mathematica just because it works fast and it does have can do some symbolic stuff for us. So yeah, so let's say that I want to look at. I'm going to get some data here, and let's get a bunch of numbers. Random, variate. I wanted to follow an exponential distribution, and the syntax is not that important, so I'm just going to go quickly. Let's say it has an average value
of 10, and then I want to have 1,000 of these values. If I spit it out, we're going to get a bunch of numbers here. I don't want to look at all the numbers, so I'm going to turn that off, right? And now if I want, one thing I can do here, I can say, give me a histogram of these data, all right? And you get this, what we normally expect is an exponential distribution. Now, if it has some little bumps and wiggles in it, it's not perfect. I go up to 10,000 data points, I'm going to get something that's smoother, right? And 100,000, notice mathematics is fairly quick on the numerics. It can give you a bunch of data here. Okay, so everybody has the idea of an exponential. By the time I got up to 100,000 data points, it's very smooth, right? Now, one thing I can do here is that there are different ways. Now, these data are binned, and we're going to get to bin data in a second. But notice they're binned, and I can get various stats coming out about these things. If I were to take the log of the vertical axis here, I would get something that looks a little bit different, right? If because there's I could take the log of either axis, but I could, in particular, the vertical one. So what I want to do is just I'll do that for you guys and we'll see what it looks like. So I'm going to go with log here, and we're doing the PDF. So, okay, so everybody sees that when I've taken the log of this thing, and now we're getting something like a linear decline here with over this space of the function. I don't know why something around to 0.4, but probably because I put this here. I'm just going to go with. There's certain different binning techniques, and I had this all written out on the previous other computer, but it doesn't matter. Okay. I can tell how many bins I want. Okay, so here I'm asking for 10 bins. You see it's a straight line on the log coordinates where it was curved in other coordinates. Now let's go look at the Pareto. So I'm just going to, for speed, I'll just copy this thing down here. And I will put in a Pareto distribution. Pareto has two parameters. Where does it start, and what the slope is. And now we'll do the histogram of this thing. Copy it down here. Let's not go with logs initially. Well, look at I asked for 100,000 variates. Let's just do this. Let's see what it says. So what's the minimum value of these variates? 1.0. I said the smallest value should be 1. That's what it's going to come out to be. What's the largest value? 81,000. Okay. So you can immediately see there's such a giant range of values. If I ask for the mean, we're going to get some kind of weird number. Mean of the data. Only 11, even though we have one value that's worth 81,000. Okay, so that's now we'll plot it here. And when we plot it, we'll plot it the first time in just raw terms. So we'll plot it in raw terms, and I want to get rid of that log thing there. And with 10 bins, we'll let it tell us how many bins it wants. And so if we have almost all the data are in that one smallest bin. Whereas, of the 100,000 data points we asked for, it's like about 95,000 of them are sitting there. So that's not very revealing just to see it that way, right? So now if let's go back to having the log coordinates here, and we're not going to get anything of interest because, well, I'll put it in do it the other way. So now, what we'll do now is we'll go to double log coordinates. I'm going to ask for the Sturgis binning, but it doesn't. So now this power law, when we have 100,000 variates in the log coordinates, it has this linear slope. Okay, and if you want to know approximately what the slope is, notice we're looking at about 5 decades of size there, right? And we're going from something on the order of 5, 8, or maybe like 10 to roughly 5 decades there. So this PDF, which I've asked for, is something on the order of -2, right? It's roughly maybe 10 over 5 in terms of how many decades are being it's crossing. Now, if I just were to ask for the CDF of this thing, right? And Bill, you can do the same thing in MATLAB, or you can do it in R or whatever, right? And so I'm gonna plot it in as a survival. So 1 minus the minus the CDF. Okay, what's survival count? And so this is going to be, let's get a linear slope in log, and now the slope is going to be something like, we have 5 decades here, we have 5 decades there, so it's minus 1. So the first thing to say is that I want to come back to my other set of slides I had here, which is say that if we look at the Pareto distribution and you take the log of it, okay, the log of the say the PDF versus log of size, you're going to get that the slope is going to be that thing, which is the same as the parameter you put in there. All right, and then if you come down here, once again, I'm not going to talk a lot about the statistics of the thing. Just trying to get a flavor for how it works. If we take that take that survival count function, and you plot the log of this thing, well, the slope's going to be just p instead of p minus 1. So the slope's going to be different by 1, and that's the basis for whether you plot it as a CDF or the PDF, you get the slope appropriately, and you got to be careful about what the exponent is, how you represent it. So, we could have called that thing just p, and then sort of p minus 1 down here. But the main thing to say is that these heavy tail data now. Go back to the Mathematica.
It's probably important to tell everybody that in much of the literature that's referred to as alpha.
Well, fair enough. That's fair enough. Yeah, and I say that what I was going to say too is that in the one prominent paper on this, which is I think it's actually it's in the front of this book. One prominent paper by Clausette, Newman, and Shalizi. It's very common to have the exponent plus 1 on the PDF.
Right.
And have just the exponent on the CDF, and then they violate that norm in their paper. Anyways, yeah. So just you have to, and maybe different software systems will have different definitions of that too. But the parameter is going to be just here I've written it as p, but commonly written as alpha.
Pareto called it alpha.
Pareto.
100 years ago, Pareto called it.
Fair enough. Yeah, that's right. Okay, good. All right.
20 years ago.
So.
Only feels like
I didn't know it.
So it turns out that what I've just shown you guys with these plots though is that think about the kind of data that we got here. We got these data, and if let's just look at some of them. We'll just see what they are. I mean, these are real valued data, right?
Mm-hmm.
And so like if you plot any of them, right, they all occur with frequency 1, and because they're real valued. I mean, the integers not, but because they're real valued. So you need it to do the binning in order to have more than count 1 for any one particular range here. So it turns out that when you're doing binning in kind of normal non-heavy tail data, it doesn't really matter too much how you do the binning. But when you're in these think about this plot here. These bins, this is a bin like size 1 to 2 and maybe 2 to 4. These bins, because there's only a dozen bins or 2 dozen bins here, they must be getting larger and larger and larger, right? Mm-hmm. So in their extent, going this direction, right? This is going. We only have 4 bins going from 10,000 to 100,000. We have 4 bins going from 1 to 10, right? So these bins are. It turns out that if you want to, when it comes time to get serious about how to estimate your data from the bin with the binning, there is this paper by the aforementioned Clausette called How to Power Law Distributions and Bin Data, and so it just gives kind of tricks and techniques for selecting the right size bins in the first place, making sure that they have the right shape and size, etc. But then also how you would estimate then the parameters when you have bins of differing sizes. Okay, so it's something to be cognizant of. It turns out that if you so basically this is a paper about a whole bunch of correction factors that you would apply to get better estimates. If you don't apply those correction factors, your estimates will be slightly off. But so I guess the main thing to say is that if you're really looking for are your data truly a power law, yes or no, you want to do these corrections. If you're just saying, are my data heavy tailed and do I have a moment problem, then maybe not so important. Okay.
But if you want to simulate the data, the system that you believe is behaving this, you need to know what alpha is. And so that's why you have to do this calculation.
That's
or the
right,
Hill
that's right.
estimator or any of the other
Start out with the data, Right, in that book, by the way, in that book that I passed around, the assertion is that the Hill estimator is perfectly satisfactory. Today we know better. There are other good ways to do it, and then particularly with the bin data, that Hill estimator can come out wrong. But anyways, make a long story short is right. This paper does have good techniques for how to estimate the parameter, which is oftentimes necessary to do further work with that. Okay, so now just to unpack some more terminology, it is commonly said that the Pareto distribution and these power laws in general are scale-free. Now what does it mean to be scale-free? And I just have one kind of quick example here. So far I had the independent variable be s, the size. What if we just rescale s by some constant k? We just say, instead of using miles, we're going to use kilometers, or instead of using, dollars, we're going to use euros or something, right? Now, in the case if it was an exponential distribution, if you change the in essence the scale, or say the exponential has a well-defined mean, it's going to be such and such. So if I change the scale of the thing, I'm going to get a different mean value, for example. But notice what happens here when on this with the Pareto distribution, or with one of these power, we have the independent variable to a power. If we substitute in this transformation into, this is now the CDF, we substitute in wherever there was an S before, we put in this is the minimum size, this is the actual size. The constant just drops out. And now this is the same distribution we had before. So it's the distribution does not depend at all on the scale of the independent variable. All right. Now, so this has given rise to the terminology scale-free, and it can be shown that these are in fact the only scale-free distributions. It's kind of these power distributions. Now, it turns out that in a total abuse of terminology, it is common to say that these distributions are scaling. Even though I'm saying here it's scale-free, right? Scale-free, the scale doesn't matter. And so some of you will know Jeff West's book on firms and cities, et cetera, it's called Scale, and he consistently uses in that book the terms, he says these distributions are scaling. Just as a footnote, back when I was a graduate student, I went to the first Santa Fe summer school, or winter school, and the talk was called, the title of the whole week was Scaling Models. All about scale-free distributions. Okay, so that once again, these are all things that evolve. These terms evolve. Nobody really designs it, right? So that's the pathology of it. See, we've already mentioned a little bit about the moments. I'm going to go on to just talk a little bit more about the moments, and just to say how we're going to deal with the moments. And I showed earlier. So now, once again, Ken has mentioned that it's usual to call this parameter alpha. I guess in our book we consistently just call parameter p. So, but this is the PDF, and then the CDF is down here. Let's use that. But here's the mean value. Here's the mean, and then the variance is this thing. The main thing to say is that notice that so for p smaller than 1, we're in trouble. Is basically the way to read this, right? So if p is 0.9, this is going to be a negative value. You can't have a negative value. The small size is x0. It says something, I think we are arbitrarily close to 0, but it can't be negative in this case. So, but now notice that, so that's for the first moment. Now the second moment, the variance has this additional thing here, which is that now the p can't be smaller than 2, where the variance doesn't exist. All right. So, and if we kept doing that calculation up to find the third moment and the fourth moment, we'd find basically that okay, for the first moment the parameter can't be smaller than 1, for the second moment it can't be smaller than 2, for the third moment it can't be smaller than 3, etc. So these distributions have the property that there'll always be some moment that doesn't exist. You'll always be able to find such a moment. So this is in some sense which you're in a world of very heavy tails when you get moments that don't exist. Now it turns out, as a practical matter, many of the values of p that we deal with in data on firms, cities, finance, etc., the values of p are between 1 and 2. That would be quite common. Many of them are quite near 1, in fact. So it's very common for this thing to kind of exist or barely exist, but this thing never exists. That'd be the norm, right? And when you say, what is it, and I can show it later on if people have not seen before, but what is the distribution of city sizes in America? Well, that has a p-value that's a little bit bigger than 1, so this is not going to be meaningful. The variance doesn't exist. Okay. Now, if the variance doesn't exist, but in fact there is going to be yes.
P between 1 and 2 for the CDF. That's the frame of reference you're using, because there's 2 and 3 for the PDF.
I hope this is not messed up, because this is from the book.
This is the P that you're using,
So,
You're using the P from the CDF.
the CDFP.
That's right, the P from the CDF,
Yes.
correct, Joe, that's right, yeah. Right, so it's right, so the PDF has got P plus one as the exponent.
So your P is equal to alpha minus one.
In the closet.
From
Compared
the-
to closet,
from
that's
closet
right,
paper.
yeah.
Okay.
Okay, so, the variance not gonna exist, what does that mean in general? Okay, what does that, what does it mean? Because we're always gonna have finite data, right? I mean, in any real world situation, or I'm talking today about data, always gonna have finite data. Well, one reaction is to say the following, is that, look, if in fact the data are real, and I apologize for the small font here, I'll blow it up if I get a chance. If the data are bounded between 0 and 1, between two finite values, we're never gonna see, for example, a city of size infinity, you're never gonna see a city of size, 10 billion people. You're gonna see maybe, 100 million or something. So we can, if you have a truncated distribution, I'm gonna make this bigger so we can just read it better. If we have a truncated distribution, then we always are going to have we always can compute. It turns out, watch this, look at the mean value here, the mean is up here, it still has P minus 1 in the denominator, and variance still has P minus 2 in the denominator, but it turns out that if you remember your freshman, I think this is actually freshman calculus, these are the P value of 2, P of 2 or P of 1, just end up being holes in the function. They're just holes, and there's a perfectly smooth distribution that's just missing the P and 1 P equals 2. So it is, well, in this case, because we have a finite amount of data, you get more complicated expressions for the PDF and CDF, but you get the fact that the variance and mean exist, okay, that they exist. Are they meaningful though, even though they exist? And what I want to show you next is argument that basically, even though they exist, they are only partially meaningful. And I'll just pull up a plot of that here, like that. This way. Okay, so we're going to go back to this first chapter of our book. We're going to look at basically the variance now in firm sizes. I've just mentioned that so firm sizes follow this power law with exponent near 1. So now this is a calculation of what the variance is, and what these many colored lines refer to is, imagine I take all 6 million firms that constitute the sample, and I start computing the variance. I just say, what is the variance? That's going to be one colored line. Okay, so imagine, look at this purple line here. I compute the variance. As I start computing the variance, instead of it converging down to something that's meaningful, it starts diverging. So watch this. Imagine we did the comparable calculation for the heights of the people in this room. Okay, so here's the variance in our heights. Okay, and there's 20 of us, 25. So we go from 1 to 25. As I go up from 1 to 25, I'm going to get some here's some mean value, and here's the ultimate variance. Say we're going to get some estimates around here, but it's going to start converging down here until we're telling us the 25th person we have a very good estimate of what the variance is. Right? Here, as we add more and more data to from the sample, the variance just keeps diverging. Now, every time we do this calculation, we end up with the same point because it's a finite number of data. They have some fixed value. These are just different paths through
You shuffled the data.
That's
As
right.
each color, you shuffled the data and estimated sequentially the
Exactly. So we have some fixed sample of data, and what you're seeing, the reason why it's going from some low value to some high value is we keep every once in a while hitting one of these big jumps. What's causing the big jump? You put some large entity in the sample, or you actually hit one of the large entities in the sample. You hit, like, you're doing city sizes, well, you hit Chicago or New York City. You're doing firm size, you hit Walmart or Exxon, and it causes this divergence. Okay. So this path here is showing how the thing is divergent. Notice I'm actually in logarithmic coordinates here. So the fact that it's diverging linearly means it's actually diverging exponentially. Right? It's going very rapidly away from it. Now, I think that Ken and I talked about this when he taught his course, that we always thought, well, this is obviously then just some noise statistic. You don't want to use it. It has no meaning. And then this past summer, some of you were here, I think, that Francois Lafont from Doane Farmers Group in Oxford came by, and they were using these kinds of divergence plots to estimate what is the exponent for the Pareto on the grounds that different exponents have different divergence rates. And I'd never seen that before.
Mhm.
And then I went back and I thought I'd only seen this kind of plot once ever before. And you might know it that it was in 1956 or 58 or something, Mandelbrot had done this plot. And
Yes.
he had actually said, you can estimate the exponent from this plot.
So the second moment's not settling in, that's how I know that, was it sugar prices or
Cotton
or
price, yeah.
cotton
Yeah.
prices, whatever, don't have a variance, have an undefined variance?
Yeah.
And yeah, and went that far as to say, and I can estimate what that.
And you can estimate it. So even though this is a noise statistic and that you end up with, the path it's taking is meaningful here. So we'll come back to that at the end if you want.
So in 625, we're gonna simulate a power law distribution. We'll do a bunch of those plots. The implication is that's your one sample, right? So this is one sample, firms in the United States, and the proposition is perhaps they're power law distributed. If you simulate, you can simulate another group of 6 million firms.
Yep.
You can simulate another group of 6 million firms. They will have the same type of plot, but they will converge to a variance that is completely
A
different.
point, right? It could be anywhere around.
Oh, no, it is all up and down, you know. So you do but if they were normally distributed, they all converge very quickly to
Narrow band.
to the same one every time you simulate your data again. So
Yeah, so just I guess so maybe the one summary way to say this is that even though for a Pareto distribution in general, with this exponent that's going to cause one of the moments to diverge, they're always going to have beyond some moment it's going to diverge. That's the rule. You can recover some meaning by going back to the fact that you're always working with a finite amount of data. Now, with a finite amount of data, it's still going to be the case that one of your higher moments, variance or whatever, kurtosis or whatever, is not going to be meaningful. It's not meaningful what this is up here. But the path by which it diverges can be useful in helping you get information about what's going on underneath the data. Yes, John.
But also, if I'm understanding that stopping point,
Yeah.
the stopping point is correct. To see if I have the right intuition about this, all right, so for any distribution, if you cut off some arbitrary part of the tail
Yep.
and rescale the rest of it, all the moments exist.
Yeah.
It seems to me then that sample size basically is determining where we've made that cut, and that should determine all of the finite estimates of the moments we're getting.
So the cut is one version of it, but also think about it though, that would be the one where imagine I have this is all 6 million firms, or maybe I have 6 million firms. Maybe this is only 1 million of them, and either I get Walmart or I don't.
Mm-hmm.
Now if I get Walmart, I end up way up here.
Yeah.
If I don't get Walmart, I end up down here. Okay. But maybe a different way to think about those is that it could be the case that imagine there's only 1,000 cities in America that are metropolitan. I always have the data, but imagine only using some sample of them. I guess you're still going to get these big jumps based on when you
get Walmart.
Just a large.
you can see where you got
cities.
Walmart on your chart for each
exactly.
color. I mean, that's when you get Walmart.
So how you chop it, I guess. I'm gonna get in a second. I'm gonna get to something called the sampling distribution for this thing. So I'm gonna hold your question to that. We'll come back to that at the end. Okay, so what I want to do now is go to talk about. We talked about truncated, and now I want to do a very similar but slightly different idea, which is called. Now I want to look at now. What are the weighted distributions corresponding to an underlying heavy tail distribution? Now, what does it mean by weighted? Imagine that we're looking at firm sizes, and Ken has a consulting company that does $15,000 worth of business every year in America. Okay, his firm has exactly the same number of data points in the firm size distribution as Walmart. 1. Okay, now it seems why do we give Axtell Consulting the same amount of weight in the economy as Walmart? I mean, those are radically differently sized things, right? So one way to do it is you could say, well, we're gonna weight this. We're gonna weight it by, for example, how many workers there are. And with by that criteria, Walmart becomes a million times more important than Ken's consulting or my consulting, right? That's one way to think about it, right? So if f of s in its underlying size, by the way, if the firm's one doesn't make exact sense to you, you also say with cities, you can say New York is much more important than Fairfax because there's more residents there. Take into account. But here's a different version where you say, look, it could be prices, and it could be a bunch of penny stocks they don't care about versus Google, which happens to keep its price at around $1,000 a share, right? So we're going to give more weight to the things more expensive. So all we're going to do here is, so if f of s is the underlying heavy tail thing,
S times that thing, it gives the weight. So for example, Walmart has 1 million employees, so I give 1 million times more weight to Walmart. Axtell Consulting has 0 employees, that's going to fall off the radar screen altogether, okay? So this W becomes now the weighted distribution. We're going to normalize it accordingly. And here this says, so this is now the density function in terms of the underlying original thing. And you know, it has this well-defined structure that all seems straightforward, okay? Now, you say, well, what does it mean and why do I want to use that thing? And first of all, what does it mean? Here's here's just an example from this tutorial that we wrote. It says, okay, so imagine I have a Pareto distributed density function. So this thing's already heavy tailed. And now this is the formula for what the weighted distribution is. And what it does, if you work through the algebra here, it actually takes it and reduces the exponent by 1. So that this basically says a Pareto distributed size distribution function, exponent alpha here, has a Pareto distributed weighted distribution function with a different exponent. That's okay. So now imagine that I hit alpha equal. So in case of firms, alpha is just a little bit over 1. So let's say it's 1.1. So now alpha for this weighted thing is going to be 1 minus that, so it's going to be 0.1. Now this thing is so heavy tailed now that now no moments for it exist at all, right? So the main way to think about these weighted things then is that we already had something that was very heavy tailed, and now I want to try to make it more meaningful because before it was not really meaningful with Walmart counting same as Axtell. So now try to make it more meaningful. Now it gets even more skewed and more hard to deal with, and it's crappier to have to mess with because I have all the data points. So the weighted function is something that is another route though to heavy tails. Right? So it's a way to get into the world of heavy tails. And now to show that it's nothing to do with continuous or discrete here, but I just wrote. We have 2 more examples. We just say, okay, so now a discrete version of the Pareto is called the zeta distribution. I'm not going to skip the details now. And then another heavy tail thing is called the Waring-Ewell-Simon. They just have the same property. That basically, as soon as you make them as soon as you go to the weighted version of them, you basically are going to decrease the power law exponent by unity. And so you're going to be in a world that's even heavier tail. Now, I think that the lognormal also has this property. You can take the lognormal, weight it. I haven't talked about that yet, but I'll talk about it at the end. And the lognormal has the property that if you take it and you weight it in this way, it also becomes more, basically you put more mass out in the tail, and so it becomes even harder to deal with. All right, I think now I have a kind of a simple, concrete example of this. Well, it's coming up in a minute. Okay. Now I thought that I thought I was out in left field with some of this stuff. I was worried that even though we make use of this in the book, so it turns out, watch this. If I want to say something like what is the typical firm size in America? The answer is the modal size is 1 employee, very small. The median size is 3 to 4 employees, somewhere in there. The average size, since there's 120 million workers and 6 million firms, the average size is 20. Well, the claim is that if you ask your local congressman, what is the typical firm size in his or her district, that person's not going to say size 20 or 3 or 4 or 1. Right? They're going to say, well, there's a 100-person manufacturing firm down here, and there's a 500-person firm over here. They're going to say the bigger firm. That's the ones they know about, right? So these things are so skewed, you can't even come up with very good measures of what's meaningfully, typical in these things. So one way to say it is that if you could ask people, you could say, as people are coming out of their plants at 5 o'clock, you could say, well, what size firm do you work for? And if you do that, what you'll get is you'll get the median of this weighted thing. Right? And the answer there is going to be then it's size 500. Half of Americans work in plants that are bigger than 500, half work in plants that are smaller. And you get that as basically the property of this weighted distribution. Okay. So it turns out that like I said, I thought we were inventing something, but if you pull out if you go into kind of like the bowels of the math probability book, you'll find this thing. It's called the moment distribution. And it basically says you can always form. I've written it here in these size terms. If this is any valid PDF, if I just compute this thing, this is like computing a moment. But instead of going from 0 to infinity, I'm going over this restricting this range here, and then dividing by this moment, assuming it exists. This thing is well studied in stat and probability, and goes by the name of the moment distribution. Basically, so
our k equals 1 is a weighted size distribution. So it hardens me to know that we didn't just come up with this on our own. I mean, it has some properties. And for example, one of the nice properties we go through in the book is that what is the class of distributions which have the property that if you start out with this being a certain functional form, Pareto, lognormal, whatever it is, you will get this thing to also be the whole thing to be the same. And so that's actually a closed class of functions. And so we go through that, but I'm skipping that here in the interest of time. Okay, last couple of things. Size-based sampling is a similar idea. And so here's the example. Imagine that you work for an airline. You're the operations research person in charge of the company. There are 2 airplanes in your fleet today landing at Dulles today. Each holds 100 passengers. In reality, one airplane has 2 passengers on it. It's almost empty. The other airplane has got 98 passengers on it, almost full. Okay. So you, as the OR person sitting in your cubicle in Atlanta, you say, well, the average occupancy of my 2 flights was 50, right? I got 100 passengers. I got 2 flights. Now imagine you're the gate attendant, and as the people come off the plane, you ask them, well, how crowded was your flight? 98 people say, there were 90 people on my flight, right? And 2 people say, there's almost nobody on my flight. There's 2 people. And so even though the true average is 50, this sample average is 96. This is just, again, the weighted distribution. And did you ever see this? The way to think about this is that what I've done is I'm sampling not on the basis of the fact that there were 2 planes. I'm sampling on the basis of the things that were on the plane, the people. So this is just so it's an example of how you get a very different answer when you use the weighted thing versus the underlying thing. So
An agent-based modeler would see this, and somebody who was not an agent-based modeler, I don't think would think this way.
Could be, Ken. Because this is the plane-specific view
Right.
of the operating researcher. This is the
Right to pick on operations research guys, because they would see it.
This is the agent view of the.
And the agent view of it, yeah.
And by the way, then this is something which this is an example where there's going to be no natural tendency to have a heavy tail here because you have only a finite number of spots on here, and planes are not going to be having. There's not one plane holds 1 million people, and another plane holds 10. Right? So this is an example where you get a quite different answer, even though it's a perfectly it's not when you would expect to have a heavy tail. And so you can imagine now in a world of heavy tails, this is going to be exacerbated. It's going to become much worse. So that's how you go from the median firm size of 3 to 4 for the underlying distribution becomes the median size of 500 in the weighted distribution. Okay. All right, I've burned up almost an hour, so I'm not going to spend much more time here. Yes, one other way to think about there are problems characterizing what is the typical value when you have one of these heavy tail distributions. Right, mode, median, mean, etc. And here I'm arguing that if you go to the weighted thing and essentially do this size-based sampling, you're basically going to get a more meaningful number. I mean, watch this. If you're asking the company, the company only had profit on average of 50 people, but most of the passengers had this experience, right? So I think this is a more meaningful number here. So now we would say, now you would ask the question, is there also a way to characterize how much variability there is? Obviously these two planes have quite different variability. So I've come up with the following thing, the following measure. I'm prepared to defend it mathematically, but I'm not sure what exactly it means. Okay, so here goes. So I want to now characterize the average value of the weighted thing versus the average value of the underlying thing. Now, so the example I just showed, the average value of the weighted thing was about 100. The average value of the underlying thing was about 50. So it's different by a factor of 2, right? But in a world of heavy tails, they can be radically different. Okay. So it turns out if you march through this thing and you show that you say just reduce these into what they are, what I end up with here is something like so this I'm calling this thing the dispersion. Right? This is how much variability there is. This is the mean of the weighted distribution is like the variance of the underlying distribution. So this is like the variance over the mean. So it's like something like a kind of like a coefficient of variation or something. Mm-hmm. But I'm calling it now. It turns out I stole this terminology, dispersity, from a different field because I found the same calculation in a different academic area. It turns out that the atmospheric scientists measure how many particles of moisture or pollen or smog are in the air, and they call that the aerosol size distribution function or something. And they also want to know what the variability of it is, okay? And so they have coined the term dispersity as a measure. And by the way, what they actually find, the aerosol guys find, is they get particles that could be like a micron up to something like 1,000 times bigger than that, and everything in between. There are particles of all different sizes that we're breathing because of pollution, et cetera, et cetera. And so, to characterize that, they call the dispersity. But now notice, so this dispersity measure now, I've written out here, so I've computed this thing now for a Pareto distribution as a function of the alpha. Alpha back to the original, what I was calling P earlier. And it has this peculiar property that so that when alpha is right around 1, the dispersity is maximal. Which is interesting because, so basically, so alpha is 2, alpha is 2, you're kind of not too heavy tailed. These things are only different by a factor of 2, that's what we saw in the earlier case I just gave you. When in fact the alpha is very, very small, these are both very large numbers, and it just happens to be that they're kind of about the same large number. But in this intermediate range, by the way, I did it for 3 populations, like one finite population, one bigger one, and then one for basically infinity. So two finite distributions and one infinite one, having infinite support. So this dispersity, though, is a measure of kind of how much variability there is in the population. And think about it, here's a different way to say it is that what kind of, when can these things be about the same? And it turns out, watch this, because if in fact I had the underlying size distribution, if it had Dirac measure, that is, if it was just a step function. So here's my size distribution. If it really was, everything's exactly the same size. So here, at this size 0, everything's exactly the same size. If everything is the same size, it doesn't matter if I weight it or not, I'm going to get the same answer. So if I have Dirac measure, this is going to be 1. But otherwise, it's going to have some value. And it just turns out that, I don't know why this is, and this is the part that we can talk about, I need some help to explain it. It looks like that the dispersity is maximized right around the exponent 1, which we all know the exponent, so I'm not going into detail here, but basically exponent 1 is right around what the Zipf distribution, for which we do seem to see lots of examples in the real world. Whether they're rare or not, we don't, we're not going to be metaphysical about that. But right around 1, the dispersity is maximized, so anyway, we have the most heterogeneity, we have the most variability right around this kind of empirical value. Okay. So I just throw that out there and
Be worth testing to see if that's actually normal.
the shape of that thing.
Yeah.
Yeah, or something similar. Yeah. Okay. I guess one of the last things I'll do here, running out of time, is that it turns out that, and once again, I did not invent this. I learned this also from the atmospheric scientists. I'm going to pull it up here now. And this is somewhat technical, but I just want to mention because it turns out lots of things work out nicely with this. So so imagine this thing is our underlying heavy tail distribution. Now one way to deal with the heavy tails is take the log of the independent variable, so when instead of go from 1 to a million, you're only going from 1 to 6. Okay, so it's bring it, kind of rein it back in. So it turns out, let's define then this as phi hat as being the corresponding PDF when we're not working in size now, but working in log size. Now remember I said before, because these things are scale free, we can't just multiply s by some constant and change anything significantly. It's going to be the same darn distribution. But if we take the log of it, we get a nice result here. The nice result is, so xi now is just log of s. And I've written it here, so this is the essential, so if I take this PDF and then here's this little slice of probability, and then say here they'll have to balance. That's the definition. That's how this is the kind of functions of a random variable here. If you do this now, you can rewrite this thing in this way. So this is I just taken this log over here like this, and now look at, so this becomes so since d log of ln of s is just ds over s, right? This whole thing shakes out to, so now this phi hat, which is the probability measure for the size distribution in log coordinates, ends up being this thing, but we've seen that before.
Yeah.
That's just the weighted size.
Yeah.
So it turns out that without going into detail, it turns out you can reduce the previously discussed weighted size distribution, which in probability is known as the moment distribution, which is also this weighted sampling distribution. All those things are just the same thing as thinking about it in terms of the log of the size. Which, so in the same way that we kind of reined in some of the heterogeneity by working in the weighted terms, you can get the same thing with log sizes, right? Okay, so it turns out now this details something which the atmospheric scientists have also done. There are a whole bunch of results now about for those of you guys who remember your harmonic analysis and Fourier transforms. There's actually a way to now do some fancy math on this thing and show that things like, well, the characteristic function of this thing is just the same as the characteristic function of this thing with some slight adjustment. I'm going to skip all those details here, and then say if you want to learn more about this, it'll be this is basically constitutes as the appendix of our book where we just show it's how it's easy to play these things. Okay, so I'm going to end it here and just say that anybody wants to know more and want to see these what I just showed on the screen. I mean, I don't have it all in kind of one slide deck, obviously, but we do have it all in one appendix to our book. And then I also mentioned that at the start that for the book that got passed around on power laws, that does exist in some electronic form, and anybody who wants that thing, we can give it to you. Okay, so I'll stop here after an hour, and thank you very much. Any questions?
When is your book coming out?
Still in production, Bill, so it's sometime mid next year.
Mid?
Yeah.
Did you mean Laplace transform? Fourier transform.
Yeah, so watch this, Ken. So S is always positive, right?
Okay.
But now ln of S is going to have support on minus infinity to infinity. So it's right. So instead of working with, I'd rather work with Laplace transforms.
Yeah.
You got to work with Fourier
You have to
transforms.
use
Go over that whole range. So there's some fun stuff to do here. For example, one of the neat things that falls out of this, which does, this is somewhat technical, but basically turns out that one of the things that falls out is that oftentimes we don't know what that is, or the data is telling us something about. We may know certain things about this, but not the whole thing. Turns out it's easier to compute some of the properties of this thing because they're more well behaved.
Mm-hmm.
So that what the appendix shows in this is
That's why you
compute the exactly work with this thing, and then you can then figure out something about that thing. Right? So, but this thing is so badly behaved. This is like a ill-behaving person who has to be. You can put them into a certain state where then they can't do certain things, and then everything works better. And in general, the moments of this thing exist.
So, the motivation for that.
Well, I guess if in fact you really care about those parameters. Then once again, I think back to what my comment at the start here was. I want to show one more thing here. Are power laws, our Pareto distributions rare or not in practice? And I'm going to tell you that I really view that question as being somewhat metaphysics in the sense of the reason why we care what it is and what the exponent is because we want to come up with a simple stochastic process to explain the data. Yes. But what if, in fact, we don't actually care, we're not trying to create a stochastic process. We're trying to create an ABM, for example. So I'm going to explain this one figure here in a second. Let's see. Okay, so let's think about the scientific process when it comes to these social science data. So we have some data. We want to explain them. So first we characterize them. And we try to say, okay, well, they can be defined by some parameter vector P. There could be some set of parameters. Now we're going to build a model, which we hope is relevant to producing these data. And so if the model can produce the same parameters, we think we've made progress.
Mm-hmm.
What I think is what we should be thinking about is, can the model simply explain the data? Right. Forget the parameters. Okay. Right. So for example, what this plot is, this is a plot of, it's hard to read the axes. This is a plot where we took 6 million Pareto distributed random variables, okay, and for each time we generated that, each dot here is for each dot is a creation of 6 million random variables, okay. We then compute what is the maximum size of the thing that got created, the biggest, in essence, firm, say. What is the median size, and what's the average size?
And you made one the min size? This was firms?
Yeah.
So the min
it's-
size is 1.
Min size is 1. So min size is 1. So basically, so generate 6 million random variables, random variables.
Mm-hmm.
Do it like 10,000 times. How many dots are here? And well, I should say, so the actual Pareto ones are the blue ones, the dark blue ones. Okay. And then we said, okay, well, let's actually do it for 2 different exponents. One is the Zipf distribution. Orange is going to be the actual empirical value that we estimated. Okay. But the Simon is basically going to be a discrete version of that same thing. Okay, and that's in
Science.
That's a light blue. And so, so for these 3, for every one of these generation processes, we produce the max, the average, and the median. Plot it. That's a point in 3 space, right? The red dot is what the US data are. And notice that none of these stochastic processes or distribution well describe the data, right? So once again, don't get too hung up on trying to figure out what is the right parameter. That's and then closet. What is the if Aaron's watching? Apologies, Aaron. Whether it's literally a Pareto yes or no. Well, what I care more about is simply can I build a model which ends up at the red dot? That's the question, right?
Yeah.
What's the red dot again?
That's the
US.
median, maximum firm size, and average of the U.S. economy. So there's only one U.S. economy.
Yeah.
And so that the U.S. economy is shown in red. And so I think that
Which one are
historically,
they all off? What is the horizontal axis?
this is log of the max size.
Log of the max size.
This is This is average size. This is supposed to be the median. Yeah.
So they're all predicting the max size is much larger than the US
That's right.
economy.
If you generate 6 million variants and you
Right, but-
those things, you're gonna get something. But they all say that
That's
instead of
right.
having Walmart be 1.5 million, Walmart could be like 6 or 8
Walmart
million.
is too small.
Right, I was gonna say that you're drawing out the joint of a very simple random process, and the US economy is
Much more
much more complex and constrained, and
There's
but it's
obviously
interesting that it's so
some
far
role.
away from any of those
Yeah.
Yeah,
lines.
Right.
You have any explanation for that?
Yeah, there's some roll.
Yeah, these are all crappy models. Right?
Well, that'll do it.
He's talked about in his paper is that there's something that constrains, but by basic calculation, the largest firm in an economy with 6 million firms, if it's power law distributed in any reasonable, should be a lot larger.
It should be almost.
Or
60
the other way
times
around,
the
if you use the formulas for determining what alpha is from the maximum
right.
size, alpha should be a lot.
Right. So now think about what did Herbert Simon do? Herbert Simon said, well, the Gibrat process was suitably modified with the Yule process running on top or whatever. Gibrat Yule type process gives me an exponent very near 1. Well, the data has an exponent very near 1. That's like I got a better explanation than I had before. Well, yes, that's better than nothing. But now what we're saying is that for the blue are the parameters for the Yule Simon. It may say right. It's different to say. It'd be nice if in fact the red ball was in the middle here. Different ball game. Right now you're saying
Yeah.
I think these may be plausible, passable models. The fact that you essentially never get that. I mean, there's something else going on. And now maybe if G. Stanley would say, he would say, well, if you look at the firm size data, there's this finite cutoff. You don't see a firm of size 6 million. It cuts off early. Okay, it's finite cutoff. Okay, so that's why the maximum is much smaller. So now we say, well, let's create then a power law with a finite cutoff. Okay, fine. But we also say, let's just build an age-based model or some other detailed representation of the thing, which actually you can just get us in that ballpark. And of course, the punchline from the book is that the same plot will then appear in chapter 17 or something with the ABM can nail it pretty close, right?
The other explanation is that it might not be a result of a power law based random process at all, right?
Right. Yeah.
So when I did my test between log normal and power law in my dissertation, they were both good fits.
Mm-hmm.
I mean, right?
Equally bad, kind of, right? Yeah.
Right, but I mean both bad, right? Both, but interestingly enough, the exponent that I had for firm sizes based on a power law model was the exact same one that you had in your in your Nature or Science paper back when, which was 1.15. And so it's amazing how both are good models. Exponents are correct no matter which data sets that you use, but then you get a result like this where you don't quite capture the exponent through the random process that the model predicts.
Yeah.
But
Well, the
And
problem
sort
you
of-
have with a heavy tail distribution, especially when what you're interested in is the few points at the very top, you probably can fit two distributions to the points you have, which are almost equally good and have vastly different predictions at the top. And getting more information about the other points doesn't really help you, because that may
Right,
not
so
tell
it's-
you about the top.
So it turns out, Doug, there's a paper floating around these days by some couple of Federal Reserve economists. So what they do is they say, okay, because Axtell's model can't quite, the Pareto distribution can't quite nail all numbers. Not only this is the extreme point, but it can't, also even like some other places where there's a slight departure. Let's start using kind of like, more and more complicated mixtures of distributions. And so of course the answer is the more and more parameters you put in for those distributions, the much better you can do, right?
Yeah.
And then you have to
Oh,
model
well,
with like, 4 or 5 or 6 or 7 different distributions mixed in. And now you have now we don't have a model though. What kind of model could produce such a mixture? We have no idea at that point.
Yeah.
So it's not useful scientifically then. At that
You get a
point,
better
I think.
fit, but you can't explain what happened.
You have no idea
Which
why.
I think is what you're doing even in the straightforward case of saying a log normal will give you the same thing. It's true, you can find a log normal to fit the same thing as the power law. But when you back up and say, what did you do for the log normal? You had a mean, and you had, a log normal has a standard deviation, and the standard deviation is orders of magnitude larger than the mean. And the fact is that it is, as the things that you see in nature, you just don't see things that have gigantic standard deviations and just little teeny tiny means. So you're really struggling to find something that would, and I would say overfitting, to find something that would not be a power law but fit the same data.
But a log normal has a simple social and random process-based explanation.
Potentially.
Right, it's a multiplicative effect. So we know how to explain that, and socially, it's actually a very good model. Better than maybe not for firm sizes. I mean, firm sizes but for other things, log normals would actually be much easier to explain.
But I skipped over, Joe. Also part of this appendix, we also have this thing about, under what conditions can a log normal mimic the other things, right? Can it mimic a power law? And I don't remember which.
That's in there?
Well, a
Yeah.
power law can mimic a lot of things without then much underlying rationale for why it's a power
Right,
law.
but I guess in log coordinates, the power law should be a straight line. The log normal can be a straight line for big sections of
chunk
that.
of it,
yeah.
Big chunk of it.
Yeah.
So I think it's a chapter. It's in this. So there's, the way that the. It's somewhere else. I don't
It
have
starts
it
to
here.
diverge around the tails, basically, the upper and the lower tail.
Yeah.
But
Right.
right around the middle,
It can follow the
it follows a power law.
the
pretty
body
well.
of the distribution can be quite similar. So anyway, yeah, so there's a, if you dig into there a little bit, Barabashi mentions this, and there's work by Huberman and Glantz, and also this older physicist named Montrol, who they figured out kind of like, if you mix log normals in just the right way, you can look very much like a power law. But we're not, there's no, we end up with no rationale for why those mixtures would have been the way they were, for example. Or to the firm size, you could say, if I have different vintage firms, each one at log normal, can that thing represent a power law? And here's the technical result. An exponential distribution of log normal distributions will give you a large body that looks like a power law.
Hmm.
So that's
I still think you're wrong.
Back to your point about the divergence of the
Yep.
exponents. So the power law model for networks right around 3 fails. Right around an exponent of 3. That's PDF alpha, not
Okay,
CDF
yeah.
alpha.
CDF
So,
2, yeah,
so
2.1.
CDF 2.
It fails in what ways, right?
So it becomes the degree distribution becomes way too skewed for it to be described
Oh.
by a
Okay.
power law. Like one node might have like 1 million connections.
I see, okay.
That like so skewed that you can't describe it that way anymore. But
There's an
right,
outlier that's.
the sweet spot where this so-called Scalefree model is defined is right between PDF alpha 2 and 3. Would that be, isn't that where your model starts? Isn't that where that starts? Where the dispersity starts? It starts at CDF alpha 1, is that right?
Yeah, so, but I think by the time you get, so I think that, I think that the dispersing will be kind of, so this is Zipf, so you're up here.
Yeah,
somewhere.
yeah.
So things are a little smoother and well behaved up there, so. Yeah, I'll have to look at the network thing, I don't know. Okay, we'll stop here. If anyone wants to more questions, I'll leave my office for another hour or two.
Thank you, Rob.
Yep, thank you.
It's not over till we close. 45 years.
45 years. Thank you.